Okay, thank you. Well, good morning, and it's a real pleasure to get to be here at iTech and share some of this technology with all of you. So I'm Giovanni Minelli, a PhD student and faculty research associate at Naval Postgraduate School. I'll be talking to you about how to automate the mission ops for very large satellite constellations. And before coming to NPS to do my PhD, I spent 5 years at NASA Ames Research Center. And one of the very first projects I worked on was NASA's first CubeSat. And so I spent those 5 years working on those first CubeSats that NASA was launching. They're out of Ames. And we heard all the arguments about how CubeSats were just a toy and it was kind of a niche and there really wasn't a future. And that was 11 years ago when we launched that first one. It's refreshing to go on iTech's website and see some of the presentations from last year, including Mike Seablum's from Science Mission Directorate, who's talking about how NASA envisions small sats as part of its future, and there's a lot of potential there. And in fact, if you look at NASA's roadmap between their science, human exploration, and space technology mission directorates, small satellites play a big role now in how they're going to gather science for their decadal surveys. So they're very much on the drawing board, and there's a few Constellation missions already funded, and there's many more in the works. Not just NASA, there's also a burgeoning commercial industry. I just read a report the other day that the small sat sector is the fastest growing sector out of this $200 billion space industry. The DoD has embraced this technology as well. That's an active area of research for us at NPS. And academia has been the longest standing member of the small sat community, both for research and for workforce development. And one of the reasons why this community has blossomed over the last several years has been because the launch capability has gotten that much better. So for example, back in February, there was a PSLV that set a world record, 104 satellites deployed. The ISS is routinely deploying small sats now, and there's other rideshare capabilities, including the one we developed at NPS called the NPS CubeSat launcher, which sat on the back end of a Centaur rocket, and over the course of 3 years deployed over 40 CubeSats. That was an interesting problem for us because we had to convince the several $100 million mission that our tens of millions of dollars of CubeSats wouldn't affect them. And that was an uphill battle to fight, but we managed to essentially disrupt that industry. And so now when you buy an Atlas V, a capability like this comes with it as a standard package. In fact, if you don't want it, you have to pay to get it taken off. That was a huge win for us in the government and the commercial industry, for the whole small sat community. We want to have that same positive disruption now on the ground segment because it currently does not exist. It needs to, because in the next couple of years, market forecasts are suggesting hundreds, potentially thousands of satellites that are coming. NASA recognizes this, and so they'll say that you can't operate satellites without automation when you start increasing those numbers by as much as what's predicted. And just to illustrate the problem a little bit, what we have, for example, on the left is an hour-long simulation of where we just generated 100 satellites. 80 of them are kind of in random low Earth orbits, and 20 of them are in a polar constellation. If you look at where those dots are flying around, and then the white dots are kind of your ground stations, on the left side, you could probably come up with an algorithm or a heuristic or an ad hoc approach for how you would communicate with those dots from the white ground stations, right? I think you could. This is what's going to happen over the next couple of years, kind of these ad hoc approaches to mission ops. Let's just scale this up by 5. So let's just go from 100 to 500 satellites. Could you, in that hour, come up with what it would take to actually communicate with those satellites? You have to automate the problem. You can't throw people at this anymore. And so we're working on this problem now at NPS. So we're developing what's called the Mobile CubeSat Command and Control Ground Station Network, MC3. And this is a distributed ground network of low-cost ground stations, a lot of COTS components. We're orders of magnitude cheaper than the bigger, more expensive, high-value ground stations. We're using, for example, the radios the transceivers cost about as much as a fancy laptop. Runs on open source software. It can handle lots of different waveforms, so as long as you conform to the frequency licenses that we have, and the hardware, the apertures use the same frequencies, we can operate these small sats. So the DoD is kind of moving in this direction already. And I can spend an hour talking about this ground station network, but this is our test bed, right? What we're doing is we're developing these optimization algorithms, and they run on the MC3 network, but because it's platform agnostic, right, we're just modeling the physics and communicating with satellites. The whole idea is to flow this into those high-value ground station networks for the government. So NASA Near Earth Network immediately comes to mind. Air Force Satellite Control Network. But hey, there's also a whole commercial piece of this as well. There's other folks out there building low-cost ground station networks, anticipating this wave of small satellites. We could work with them as well. But what's been great about iTech is that it's forced us to think about other applications too. And so because we're platform agnostic, we're just modeling physics and we're tracking, before I get into the algorithm, I'll just tell you a little bit about it. We're tracking objects that are moving around. But why not invert the problem, and instead of pointing ground antennas at satellites, why don't we point the spacecraft at the ground? And so we can we can optimize how many images we take per ground track. Wouldn't that be neat? Or apply it to drone swarms, as you're coordinating swarms of drones that are flying around imaging a field, for example, doing remote sensing. Or self-driving vehicles. There's a really bright future in this with these kinds of algorithms. So the current state of practice, there's a lot of optimization research that's been done over the last many decades. So if you think of, for example, the traveling salesman problem, that's a very well-studied problem. Turns out there's actually no solution to the traveling salesman problem when taken in full context. You have to reduce the problem down, and then you can actually run an optimizer and solve the problem. So, and this is very effective. This is how airlines route an airplane across the country optimally. This is how a package gets delivered from point A to point B overnight. So there's a huge industry for these algorithms, but by reducing the problem down and simplifying it, you get rid of all the fun stuff and you lose performance potentially in those areas. So just to illustrate the point a little bit, oh darn, and I wish our second video would be showing here. But in any case, I'll just move quickly through the slide then. On the left, what we were going to show was a simple Eigen Access maneuver. And so this is from real flight data from the NASA TRACE satellite. And basically what's happening is the industry standard maneuver is just going between those 2 points and plotting the arc between the 2 points. On the right, if you can model the moments of inertia, the angular momentum of the system, solar wind pressure, atmospheric drag, make the model arbitrarily complex, you can run an optimizer on this, a physics-based optimizer, and get these really non-intuitive slews. And actually what will turn out is you can get there quicker and use less propellant. And so this is verified with NASA satellites. And actually this has also been done with the ISS. So they maneuvered the ISS back in the mid-2000s using these kinds of algorithms. And so fundamentally what happens is, in our case, we're modeling our satellites as benefit value bumps, benefit value functions. And the more value the satellite has, the bigger the bump. And so what can you do with that? Well, you can formulate the problem with essentially 3 steps: the objective function, the dynamics, and the constraints. And that math looks pretty complicated there, but it's actually pretty simple. That first line is your objective function. What are you trying to maximize or minimize? So do you want to maximize profit? Do you want to minimize propellant or energy? In our case, we want to maximize data from the constellation. That next line is the dynamics, so the orbital mechanics of the satellites, the ground station location, the kinematics and the dynamics of the ground antenna itself just moving around. And that last little piece is the constraints of the problem. So what are your starting and ending constraints? What are the antenna limits, for example, position limits? And what's your planning horizon? When do you start and stop? And you can map this, for example, to something as simple as link margin. As the satellite gets closer to the ground station, the bump goes up, your signal strength is better, communicate with the satellite. But what else can you do with it? You can snap a picture, let's say, and if you really need that, get that picture down tomorrow, make the bump bigger. Well, let's say you snapped the picture last week and it's no longer relevant, the bump goes down. And you can throw a whole lot of things into how you scale those benefit value functions. So here's a very simple example of 4 satellites passing over our Albuquerque station. 3 of those are simulated, and actually that yellow one is a real one, because we don't have hundreds of satellites to test with, but we do have a couple, and we do have ground stations to go with them. So we'll track one satellite, and then we'll track the other, track the third one, and so on. So if you look at the simulation for how this works, this makes sense, right? The contour plot corresponds to each satellite, and then that red circle is where the antenna is pointing. So this makes sense, right? We track one satellite, we break off, it'll move over, track the second one, and so on. But here's what's actually happening. This is kind of a sped up video of the ground station antenna. It's working really hard. It's moving upside down, it's unwinding, it tracks the first satellite, then it breaks off, hits the next one. Oh, and by the way, that was a real satellite, so we got real data from that pass, and then we move on and move back into the simulation. So we've done this now with 2 real satellites, 2 real stations, and the rest scales up nicely in sim. So who's working on this problem? So for myself, this is my dissertation research. The members of my committee are also my team members. And so we have Professors Mike Ross and Mark Karpenko from the Control and Optimization Lab. So they've done a lot of this work with optimizing slews of spacecraft, and this is kind of a new venture for them into the ground station part of it. And so Mike Ross, for example, has written the book on pseudospectral optimal control. Brilliant folks to work with. And then we have Professor Jim Newman, who has spent over 20 years of NASA service, notably in the astronaut office, and then after retiring from NASA, has spent over 10 years now developing CubeSat infrastructure, both on the ground segment, on the launch side, and then also standardized CubeSat buses for the government. So without a doubt, the right folks are looking at this problem. How do we flow this technology out of our little research area, out of our lab, to the rest of the industry? So because we're government research, we can do government-to-government tech transfer very easily. And so for NASA, for example, if they were interested in this, this would be free for them to use. And if we wanted to do sponsored research with NASA, we have a very simple mechanism to do this called the Military Interagency Purchase Agreement, the MIPR. And so we could get started on this really in the next couple months. This is actually a very interesting, this is why this research exists, is we want to make it relevant to other government users. But there's a whole other piece of this, the commercial side, that we've actually become very interested in through this NASA iTech initiative. And so if a company wanted to come in and use this, they could enter a cooperative research and development agreement with us, a CRADA, or if they wanted to license the technology themselves, they could take it and run with it. But I think most interestingly, we could also work on spinning off this technology. And so that's something that we can talk about a little bit more during the roundtables. Certainly an interesting proposition. At the end of the day, the IP belongs to the government. We have 2 patents, one that's already been issued, one that's in the works right now. And really what we want to do, what we're asking for, is to work with NASA. We want to cut our teeth with these algorithms and implement NASA's requirements, and basically define the requirements, implement the changes in the optimizer, and then we can start doing low-risk simulations using then assets, both the ground station and the satellites, these high-value assets, in sim until we buy down the risk, and then we do an actual demonstration. I think at that point, we'll have an optimizer version 1.0 that we can start sharing with other folks, with the industry. And the reason why we want to start thinking about this is, so for example, now NEN operates about 40 satellites with about 20 ground stations. If you look, there's about 10 or so people per mission running this. Let's just double that number. So, because the NEN folks are busy, right? So let's just go from 40 satellites to 80 satellites. What do you think is going to happen? Well, some people might start getting bumped, right, with these passes, going to get even busier. So let's say you have a 10-minute contact, one of these beautiful antenna sites, 18-meter class antenna site, 10-minute contact, horizon to horizon. Usually the way it works is you'll take one pass and then bump the other one if there's a conflicting pass, right? What I would propose is actually take one pass, break off 5 minutes in, and then take the second contact. But then now you lose 5 minutes of capacity, right? You need to get that capacity back. Well, what we're doing is, by the way, those stations are over $6 million a piece. So if you wanted to add 10 minutes of capacity to the network, you'd be spending potentially a lot of money. What we're proposing is instead you would spend about $100,000. That's what we're spending on our ground stations. And you get about 2 minutes of contact time. The dish is small. It's a 3-meter dish. The link margin isn't as good. So you only get 2 minutes of good contact time. But now for $100,000, you can build 3 stations around the country, and then you can get your 6 minutes of capacity back. So, but you need an optimizer to tie it all together. You can't just throw people at the problem. You have to look at automating. So consider this as the CubeSat of the ground network, right? Just the way CubeSats are augmenting the expensive missions, right? CubeSats never replaced Hubble and ISS, but they're augmenting those missions, right? And so likewise, we can do this with low-cost ground stations and the optimizer to go with it. So we think, you know, we can very quickly start increasing the capacity of these networks. So what could we do? Just a quick schedule. We really think if we got started on this, you know, in the very near future, we could do demos with NASA, and by 2018 have a product that we could start making available to folks outside of our group. And so at that point, if you wanted to talk about commercialization, that's when that product would come out. Then I think once we started looking at that, you know, specifically after the ground stations, we'll start integrating the satellite imaging problems, the drone optimizations, terrestrial vehicles. I think there's a really bright future in in this field. So our last kind of takeaway here is that we're platform agnostic. We want to start with the ground stations, but really we want to expand out to all these other potentially really interesting applications. And so this could start right here at iTech. So I appreciate your time and your consideration. Thank you.
So I noticed a few functions you're proposing to automate, and your title claims it's autonomous operation of the full constellation. However, I'm only seeing contact planning and arranging for the communication downlink and uploads. What other functions are you automating that are necessary for the management and operation of these fleets of satellites?
So, okay, very good question. Right now, we're starting with just the centralized scheduling and optimization of the ground stations themselves. So right now, the way most of these networks operate is in a bent pipe fashion, where these satellites are built by different people, different software, different ConOps, different stakeholders. We're going to keep that bent pipe model because that's not going to change overnight, right? So immediately, the impact what we can have here is by automating and breaking off and tracking multiple satellites in that same contact window. That's the immediate benefit that we can do. As we move forward, then we can start talking about more automated process on the command and control side themselves. But that's not going to change overnight. That's going to take a long time for us to do. So really what we want is to keep that bent pipe capability active, but we just want to maximize that time.
Can you tell us who's your competition for doing this?
So, okay, let me start by saying this is government research, and so our intention is not to compete with the industry initially, right? What we do is we identify gaps where we can have value, right? And so this is a gap that exists within the government where we're going to add value. If we were going to commercialize this, the competition out there, there are folks, and there's some publications out there, there isn't much, but they have applied optimization algorithms to their networks as well. The difference being that every implementation was kind of like that traveling salesman problem I mentioned earlier. So the heuristics that take down that problem into something that's solvable are usually proprietary. So it's hard to understand exactly what those need to be. That's kind of why it'd be nice to start working with NASA first and developing this as a government-to-government technology, and then we can start pushing it out. And then you're solving the needs of those commercial folks as they come up.
Sorry, when did you leave Ames?
Just right at the end of 2011.
Okay, thank you.
Yeah, and looking at your algorithm there, it's highly nonlinear, and you didn't talk anything about the size of the problem, the number of variables, the number of constraints,
Sure.
Just an order of magnitude, whether you're talking about, say, 40 satellites and 20 ground stations. How big is this problem? What's your solution technique for the nonlinearity?
Sure. So the way the optimal controller, the actual optimizer works for this, its nonlinearity is built into it. So it doesn't matter if it's linear or not, which is kind of nice. In terms of scaling, of course, the more nodes you add into this solution, the longer it's going to take to solve, right? So if you have thousands of satellites you're going to track, it's going to take some horsepower to compute that. However, the scaling of this problem, what we see is scales linearly with the number of nodes that we add. If we were going to go down with this other approach with the mixed linear integer solution, those scale as a function of n squared. So it scales exponentially. That's why you have to start simplifying the problem down. That's why our models can actually be arbitrarily complex, and we can still solve them in a sufficient amount of time. Okay, thank you.